All right, well, today there's two lessons because there's a very interesting link between simple harmonic motion and uniform circular motion, something we studied already in some previous work we've done together. So let's start this object moving here, and it is an object which is at the end of, you could think of an imaginary string here or some type of gravitational field, doesn't matter. It's some object moving in a circle. So let's get this object moving in a circle. There you have it. Object moving in a circle. It's the blue dot. Well, the blue dot of the circle also has components to it. It's a position ordered pair. Look right there. That's a position ordered pair. Now what I can do is I can focus just on the X component of that ordered pair here, and I could focus just on the Y component of this ordered pair here. So let's do that. Let's just focus in on the X component of this object undergoing uniform circular motion. Let's do that right now. So look what's happening here. The object goes over, stops, comes back the other way. Stops, comes back the other way. Kids, the X component of uniform circular motion is simple harmonic motion. Similarly, let's focus in on just the Y component of the position vector for this object undergoing uniform circular motion. Look what's happening to the Y component of it. Goes down, stops, goes back up, stops, comes back down. Lo and behold, surprise, 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 the Y component of an object undergoing uniform circular motion is simple harmonic motion. So uniform circular motion can be thought of as simple harmonic motion X component combined with simple harmonic motion Y. Sorry about that. So as I was saying, uniform circular motion is a combination of X component simple harmonic motion with Y component simple harmonic motion. So what we want to do now here is really take a deep dive into the mathematics to prove the connection between uniform circular motion and simple harmonic motion. So if we take a look at an object undergoing uniform circular motion, here's a circle, it's moving around here, all right? And what we have here is where it's at this point right now. So at this point right here, we're going to say that it is a distance away from the center, which we know as the radius, and I'm going to call that radius A, okay? Because that's as far away as it always is. It's its maximum position away from the center. So it's a good idea to call it A because that's related to the amplitude. So when it's at this position right here, when it's at that position right there, we can say that its position is the X component of A and the Y component of A, right there. And at that spot right there, we know that there is an angle between X and A, and we're going to call it theta. And we know that when it's at that position right there, Y will be perpendicular to X, so I can put in a right angle there. And this would be the complementary angle to theta, and I'm going to call it, I'll use the Greek letter omega right there. So we've been talking about the position of this object as it moves around in uniform circular motion. It's at a radius A always, and when it's at that position right here, I can assign an X component to it, and I can assign a Y component to it, just like in the animation we just finished watching. So as it's moving around, Since it's uniform circular motion, I'm going to say that its velocity is v naught. And at this point right here, its velocity would be in this direction. Then it swings over to here, and when it's at that point right there, it still has a velocity v naught, but all of the velocity is in the x direction when it's at the very top here. All of the velocity is in negative x direction in this particular case right here. So the y component to the velocity is 0. Then it swings through here. Swings through here. At this point right here, all the velocity is straight down. It still would be v naught. The magnitude does not change, but all of the velocity would be in the negative y direction. So at this spot right here, its x component of its velocity is 0. Then it swings through here and it gets to here, and its velocity is v naught in this direction. But in this direction, that's positive x. So the y velocity component, when it's right here, right underneath the center, okay, its y velocity of the component is 0. It swings through here, gets to here, right over from the center. At that spot right there, it has 0x component velocity because it's going straight up, straight y, straight y. So its x velocity component is 0, and it's moving in the y direction at a v naught velocity. So yeah, so what I just described here was the top view of a object undergoing uniform circular motion. So think about you being hovering above this circle, looking at this object going around in the circle. All right. Now what we're going to do is we're going to look at it from the end, as if you were down here when you look at it from the side view. From the side view, what you would see is the object goes over and it comes back. The object goes over and it comes back. Very similar to the animation we just looked at. All right. So that's what I've drawn here, side view. The object goes over, stops. X velocity is 0. The object comes back, stops. X velocity is 0. And right in the middle, at this spot right here, and in this spot right here, all of the velocity becomes x component velocity. X component velocity. So since all of that velocity is now an x, we can say that at the middle here, it's at its maximum x velocity. And we can also say, hey, look, this side view is nothing more and nothing less than simple harmonic motion, as we saw in the animation that I shared with you earlier. So here we are now, and what I've written down here for you is the equation that I had in the previous lesson from today. And it says that the velocity of an object at any point while it's undergoing simple harmonic motion, its velocity is equal to the velocity that it has when it is at a maximum, and we know that that's v naught, all right, that magnitude never changed, times what we have in the bracket here, 1 minus x squared. What is its x position? What is its x position as it's moving back and forth? All over amplitude squared. What is amplitude? Remember, amplitude is how far it is maximum from the rest position. How far is it maximum from the rest position? That is an equation we had from simple harmonic motion. What we can now do is say, well, look, that's simple harmonic motion. This uniform circular motion, its x component is simple harmonic motion. So let me rewrite that as velocity x component squared is equal to that expression. Since I know that uniform circular motion is a combination of, uniform circular motion is a combination of simple harmonic motion x component, simple harmonic motion y component, as I've shown you here, and as we saw in the animation that we shared earlier. All right, we're back here. Let's take a look more deeply at this velocity here in this direction. It's got a magnitude v naught. At that spot right there, I can take that velocity vector and I can break it down into its x component right there and its y component right there. As any vector we know, exists, if I put that vector on a xy reference frame, I can break it down into x component, y component. Now let's have some fun with angles. If I know that this is omega here, look, I've got another 90 degrees going on right there. There's 90 degrees in there. So if that's omega and I want to complete it to 90, I know I have theta there. It's the complementary angle. All right. Now look here. There's another 90 right there. Another 90 right there. So if this is theta and I want to complete this 90, its complementary angle would be omega. Now I'm in this right angle triangle right here. Right angle triangle. So I know there's 90 degrees in here. If I have omega here, I know to complete the other 90 of a 180 triangle, I need the complementary angle to omega, and that would mean that theta is right here. So through this sort of itsy bitsy spider went up the spout, I have shown you that theta is here, but it's also right here through the concept of complementary angles. Complementary angles within these two triangles have helped us establish that the triangle AXY is similar to the triangle V0, VY, VX. This is a complementary, these are similar triangles. The triangle V0, VX, VY is similar to the triangle AYX, similar triangle. All right, so we're back here and now we're taking advantage of the fact that these triangles are similar. So since they're similar, we can set up ratio of the appropriate sides. And we know the sides are appropriate by finding what angle they're opposite from. If I am careful about looking at what angle they're opposite from, I can establish this ratio of similar sides within similar triangles. Vx, velocity x component, divided by V0, the whole velocity, the hypotenuse of the triangle, is equal to the y component of the position of the object as it goes around in the circle, divided by what I'm calling a, the amplitude, which is also the radius. But by Pythagoras, if we go back to the triangle, by Pythagoras, look at my triangle there, I know that a squared is equal to x squared plus y squared, or y would equal the root of a squared minus x squared. So let's replace y with that. And I put it in here. Okay. Now I'm going to SBS. I'm going to SBS you. I'm going to square both sides. So let's do that. Vx becomes Vx squared. V0 becomes V0 squared. I'm squaring the numerator. Squaring a root gets rid of the root. So I'm left with a squared minus x squared. And in the bottom, I have a squared. So let's do some fancy mathematics here. What I'm going to do here is divide each term in the numerator by a squared. And look what I have. A squared by a squared leaves me 1. X squared by a squared leaves me with x squared minus a squared. And then what I'm going to do is I'm going to multiply both sides by V0 squared. So if I multiply this side by V0 squared, it cancels out, and all I have is Vx squared. If I multiply this side by V0 squared, I have this expression right here. Oh my goodness, that's exactly the same as the expression that we came up with for velocity of an object undergoing simple harmonic motion. So what have I done here? I've proved to you simply from the geometry of uniform circular motion that the velocity x component of the object undergoing uniform circular motion is absolutely positively the same as the velocity of an object undergoing simple harmonic motion. And I could go through exactly the same argument for Vy. So we proved it to you before just by kind of looking at the simulation and looking at the object moving about, but this is a mathematical proof that proves that uniform circular motion is simply simple harmonic motion x component plus simple harmonic motion y component. All right, well, let's use the power of what we know from uniform circular motion and the power of knowledge of simple harmonic motion to come up with a really interesting conclusion here. Remember all the way back into grade 11, speed is equal to the distance you travel divided by how much time it took. Well, the distance around a circle is 2 pi r. And to go around once is called period. Let's rearrange this equation and we get time is equal to speed divided by distance. Well, there's our circumference 2 pi r. But in the example we just had, the radius was a. And the speed with which it was moving around the circle was not just any v, it was v naught. Now, let's recall from simple harmonic motion. This is an equation we came up with earlier today. V naught squared is equal to the spring constant divided by the mass all over the amplitude squared. Let's divide each side by V naught squared and then multiply each side by m over k. I'll let you work on this to see how it becomes this next line. It's good for your brain. And we have amplitude squared divided by V naught squared, the speed squared, when it is at the rest position, is equal to m over k. And I'm going to square root both sides. So I have a over v naught is equal to root mk. This equation here I called a. This equation here I called b. Let's substitute b into a. Let's substitute b into a. So look what we have here. I have a in the numerator, v naught in the denominator. A in the numerator, v naught in the denominator. So I can replace that a over v naught with root mk. So if you ever want to know the period of something undergoing simple harmonic motion, the period is equal to 2 pi root the mass of the object over the spring constant. How did we come up with this equation for the period of an object undergoing simple harmonic motion? We used our knowledge of uniform circular motion, our knowledge of simple harmonic motion, and realizing that there is this connection between them. So a lot covered today, kids. Try your best, ask me questions, 2 video lessons today. We'll get through it. We'll be patient. Just like before, if you got a question from the homework that I'm assigning today and you want me to take it up, tell me. Go to the discussion thread, and I'll take it up for you. Be safe. Take care of yourselves. Be patient with each other. Please let your classmates know I'm active on here. Take care. Bye-bye for now.